Hello everyone. Thank you for joining us. Today my colleague Majdi and I will discuss about design challenges associated with an axial flux permanent magnet generator. In addition, we will focus on what EMworks has to offer to tackle such challenges and what kind of simulation studies can be performed using EMworks software solutions. Today from EMworks team, Majdi El Fahem and myself Cal Dasaroju will be presenting this webinar. Before discussing our today's agenda, let me introduce us. My name is Cal, and I'm working as an account manager for EMworks. I primarily handle commercial sales and marketing activities for our company. My colleague Majdi works as a senior application engineer and technical support expert. He is an experienced user of EMS and EMworks 2D software and has extensive knowledge in the field of low-frequency electromagnetics. Feel free to write down our details to email us afterwards for any inquiries. You can also connect with us over LinkedIn. Moving on to the agenda of today's presentation, I will be discussing briefly about our company EMworks and the products we offer. Then my colleague Majdi will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMworks for its users. So let's take a quick overview about our company EMworks. We offer 3D and 2D electromagnetic simulation software as an add-in tool for SOLIDWORKS and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. In addition, our products are gold certified by Dassault Systems SolidWorks Corporation since 2008. As you can see on the screen, we have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany. Now let's talk about EMworks products. We offer 4 products with various add-ons covering frequency range from DC to light. Our first flagship product is called EMS, which is used for electric and magnetic field modeling for low frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, actuators, circuit breakers, transformers, and electrical machines. Our second product is called HFworks, which is used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, waveguides, etc. Our third product is called EMworks 2D, which offers static analysis and covers simulation of planar and axisymmetric geometries. Our latest addition in the suite of electromagnetic simulation software is the product called as Motor Wizard. This is a template-based motor design software. It offers analytical and finite element analysis of brushless DC electrical machines. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, you will see few simulation results which has been achieved using EMS for SolidWorks. Now let's take a quick overview about our licensing structure. EMworks offers 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the programs, our licensing structure is usually annual based. The topic for today's presentation is design challenges and solutions associated with an axial flux permanent magnet generator. Through this webinar, we will learn three things. Number one, advantages of axial flux machine over radial flux for certain scenarios. Number two, we will study about the applications of axial flux machine in different industries. And finally, we'll look at the design challenges of an axial flux permanent magnet generator and few simulations performed using couple of EMworks software products. Before moving to the technical part of the presentation, I would like to highlight few points. Kindly mute your microphones to avoid any background noise. You can use the GoToMeeting chat window to type in your questions and we will answer them at the end of this presentation. A webinar recording will be sent to all the registrants in few days. Now I would like to request my colleague Majdi to take over and present the next part of this presentation. Thank you. Majdi, over to you.
Thank you, Carl. Let me share my screen. Thank you, Carl. Hello, everyone. My name is Majdi. I am a senior application engineer at EMworks, and I'll provide the technical part of this presentation. In today's session, we will go through electric permanent magnet machines and precisely the axial flux permanent magnet generator. Now, let's have a look at the agenda of our presentation, which will be started by an overview about radial and axial flux machines. Later on, we will have quick comparison between those two machines. After that, we will talk about some applications where axial flux machines are used and for what reasons. The remainder of this presentation will be dedicated to treat the challenges and the issues posed by axial flux permanent magnet generator. We will see how EMS and SOLIDWORKS both will be used to tackle these design concerns. As many of you know, electrical machines can be classified in two categories, which are radial and axial flux machines. Radial flux machines are most known and used for a long time. However, axial flux machines are not relatively new, but their use has been increased only during the past 2 decades. The difference, as their name implies, that in axial flux, the magnetic field direction is parallel to the machine rotation axis. And this is opposite to the radial direction in radial gap machines. It presents several topologies like the double-sided rotor axial flux permanent magnet machine or double-sided stator. It comes also with or without iron cores. Figure 2 shows EMworks axial flux permanent magnet machine developed by the Belgium startup Magnex, while in figure 3 we can find the typical radial induction motor. In the second part, as we mentioned at the beginning, we will go over a comparison between radial and axial flux machines and the main advantages of an axial flux machine. We will start by the difference in the magnetic field path. In the radial machine, the flux path is much longer than axial flux machine because it goes from one rotor pole to the first tooth in stator, then through the stator back iron to the second tooth of the stator until reach another rotor pole again. Opposite to the radial machine, the axial flux machine has shorter and direct path. It goes directly from one to another pole through the air gap. The magnetic field remains strong along the shorter path, which help to increase the efficiency and the power density of the machine. In figure 4, we can see 2D simulations that show the magnetic flux path and directions in both machines. These 2D simulations were done using EMworks 2D inside SOLIDWORKS. The axial flux machine has several advantages compared to the radial flux machine. It provides a high power density and torque with a limited machine size. To validate this, we have used 2D and 3D electromagnetic simulations to analyze radial and axial flux generators. The simulated radial machine is the anterior permanent magnet synchronous machine used in the 2004 model of Toyota Prius, while the second machine is a 24 poles double-sided rotor axial flux permanent magnet machine. The model's geometry were seamlessly created inside SOLIDWORKS, and the simulations were conducted using EMS coupled to SOLIDWORKS motion. As can be seen from figure 7, both machines have closed diameters, but axial flux machine has 50% less in terms of length and 30% less in terms of weight, but it provides higher output voltage. As a conclusion, from what we have done, the axial flux machine produces higher output voltage with less material and reduced size. The axial flux machines are used in several applications and fields. They are used to drive and power electric vehicles due to their lightweight and limited size. They can be used with less mechanical gears and transmission systems as direct drive motors because they are able to provide high torque at low speed. They can be used also as a generator for the high frequency systems of ships and aircraft, since they can have high number of poles with a compact structure. In addition to those, water and wind turbines use the axial flux machines due to their high efficiency and low maintenance costs. Axial flux generator used for wind turbine can reach an efficiency of 96%. As we have seen, the axial flux machine is superior than the radial flux machine, but it poses more design and manufacturing challenges and issues. Therefore, in the upcoming slides, we will focus on the axial flux permanent magnet generator and see how EMS for SOLIDWORKS can help to solve those issues and give some solutions. The main design keys of an axial flux generator are the performance, the efficiency, the power density, and we need to know how it operates under different load types. We should study these different aspects of the machine before going to the manufacturing phase. To achieve this goal, we have to start by creating a CAD design of the machine. Choose an initial topology, whether it is a double-sided rotor or a double-sided stator or a multi-stage machine, and this choice depends on the length of the machine and also on the weight, both of them tolerated for the machine by the application. The size of the machine can be determined depending on the application and the budget. Like in electric vehicles, the size is crucial and should be limited as much as possible, while it can be tolerated in other applications like wind turbines. For this reason, SOLIDWORKS CAD software can be used to design the machine. It offers an intuitive and flexible CAD solution. Several features can be used to optimize the structure and increase the productivity. This is from a geometrical point of view, while from the other side we should think about the material will be used for the machine. We should think about the material used for the steel, for the ferromagnetic steel cores, and also for the magnetic poles. Also, we have to think about the speed, whether it is high or low, the electromagnetic losses that can be generated by the machine during its operation, and any losses will be automatically converted into heat. The axial flux machine has a weakness point related to the high axial forces exerted in the ferromagnetic course. This is why we have to see the mechanical stresses. To handle all these analysis, an electromagnetic solution with multi-physics capabilities is needed, which is EMS inside SOLIDWORKS. These are the main design challenges of an axial-flux permanent magnet machine. To conduct the performance analysis of the axial-flux permanent magnet generator, we have to start by the no-load analysis. Predict the output voltage of the generator using different magnet types, then calculate the voltage versus different speeds, and study the short circuit response of the generator. Later on, we have to evaluate the generator function under different loads, compute the electromagnetic losses including winding, iron, eddy losses, simulate the generated heat caused by these losses, and estimate mechanical stresses caused by magnetic forces. Now we will have a quick review about EMS environment. EMS is a SOLIDWORKS add-on, which means that it is fully embedded inside SOLIDWORKS and has the same look and feel of SOLIDWORKS. Here is the 3D model of the simulated machine. It is a double-sided rotor with 24 poles and a coreless stator. Let's move to EMS tab. It is based on a simple and easy user interface. Let's create a new study. Just right-click on the assembly name, select study. In this property page, we have six modules, 3 for magnetic simulations and 3 for electric simulations. We have also the option of parameterization, which allows to parameterize whether geometrical or simulation variables like current, frequency, and so on. We have also the coupling analysis options. EMS studies can be coupled to thermal, structural, motion, or circuit simulations. Let's choose now transient magnetic module coupled to motion analysis. Select motion study and select the moving parts, which is the rotor, and the band, which is made to separate the moving and the fixed parts. A new study is loading. After creating the study, we can start by applying the material. We can apply the same material or one material to several parts using the option of multi-selection. Apply material. A rich and well-organized material library is shown now. We will select our material, which is neodymium 42. For the magnets, let's see how to apply the magnetization of the magnets. Just right-click, coercivity direction, and it is the same. We can apply the same magnetization for several magnets using the multi-selection option. We have here the different coordinate system, and we can also use a local coordinate system. Let's go now to the second part, which is the coils. We have two options, whether it is solid or wound coil. In our case, in our simulation, we will use wound coil. We will select 3 coils for one phase. We will select the entry phase of the coils. It is quite easy and simple. Just select order and define the entry ports of the windings. Since entry and exit ports are the same, we can check this option. Now we'll move to the general properties. It contains the property of the wire diameter, the conductor diameter, the number of turns, and whether the filling factor, and also the coil type, whether it is current or voltage driven coil. Let's suppose that we have 20 turns per coil, so it is 20 times 3. We can adjust the wire gauge number or the diameter of the wires. Let's say, for example, 0.2. As you can see, the filling factor changes. Let's go here. Now you see the excitation types. We have DC current, sine wave current, and we can also import current from text or Excel file. validate. This option helps to define or allows to compute torque or force in selected entities. Also, EMS comes with a flexible measure. It contains several options, like you see here. And also, it allows to specify the mesh element size in specific parts. Like, let's suppose we want to have only 2 elements through this or through these permanent magnets. So we should select all the magnets and specify the maximum element size. In our case, the magnets have a thickness of 9 millimeter, and we want to have 2 elements only across their thicknesses. So we should put 4.5 millimeter. Now let's have a look at EMS circuit simulator. We have an example of schematic here. It contains the 3-phase windings with RLC loads. This is from EMS side. Now let's move to SolidWorks motion. We have an example of SolidWorks motion study. We need to choose motion analysis. It allows to define motors, springs, dampers, force and torque, mechanical contacts, and gravities. All these parameters are allowed by EMS coupling to motion analysis. In our case, we use a constant speed motor, rotary motor, with a speed of, for example, here it is 1000 RPM. Let's see the rotation of the motor. From SolidWorks motion study, and we have also the option of multi-configuration that can be used in this case. So we have around 2 configurations to design 2 machine designs, one machine with 24 poles and the second machine with 48 poles. So we can show the configuration or activate the second configuration and see that the rotors will have 48 poles instead of 24, and we keep using the same model. Okay, this is from EMS environment. Let's go back to our presentation now. Now we are back to talk about the no-load analysis. The open circuit simulation using EMS can be performed by the circuit coupling feature. The simulated Axial-Flux machine is shown in figure 8. It is coreless double-sided rotor machine with 24 poles. It means that it has no core in the stator. 2D simulations were obtained using EMworks 2D. They demonstrate the magnetic field lines of the machine magnetic circuit. However, the Axial-Flux machine has a 3D geometry, but the 2D approximation can be used to get an idea about the magnetic field strength and its path. It helps also to study the best magnets arrangement able to generate higher power density. EMS coupled to SolidWorks motion was used to run the open circuit simulation. The induced voltage results are illustrated in figure 11. They represent a sine wave shape with a peak value of 39.8 volt and a frequency of 120 Hz. The speed is 500 RPM. To get an idea about the relation that relays the output voltage and the used magnet in an axial flux generator, a series of simulations were conducted using EMS coupled to SolidWorks motion. As can be seen from the 3 figures of this slide, the output voltage is maximum when the neodymium magnets are used compared to ceramic and cobalt magnets. But this is not sufficient to make this select of the right permanent magnet, because this choice should depend also in other criteria like the operating temperature of the magnet and its corrosion resistance. The cost and the mass also are 2 important factors. The generator speed can be involved and we will see in the next slide the reason. EMS was used to compute the output voltage at different speed rates, and we got the results plotted in figure 15. It can be concluded that the voltage is proportional to the speed. So if the designed machine will operate at high speed, low resonance permanent magnet might be used to avoid any overvoltage in the system. In other contexts, a machine designer can think to add more stator and rotor cores to increase the output voltage at low speed, like in multi-stage machine used for wind turbines. Before prototyping the generator, we need to know the impact of the speed on frequency of the designed machine. For this purpose, we use two different machines. The first is a single stator Axial-Flux Permanent Magnet Generator, while the second is a double-sided stator machine. Using the multi-configurations feature of SOLIDWORKS, we were able to run both designed machines within the same model. First, we have run the double-sided stator at different speed to see the impact of the rotor velocity on the frequency. We can see from figure 17 that at 500 RPM the generator produces a signal with a frequency of 200 Hz, while at 1000 RPM the frequency of the output voltage is 400 Hz. These generators are suitable to power ships and aircraft systems. The second scenario was to run at low speed both machine designs. As we can see in figure 18, we can get more power by adding additional stator core. The size of the machine is still compact. Since we have raised the point of the overvoltage that can happen in case of high speed operation and can damage the machine as well as the system, the short circuit response should be also studied to have an idea about the high current can be produced at this case. The schematic of the short circuit simulated in EMS is shown in figure 20. Now we can see that the short circuit currents are too high and almost 10 times bigger than the normal operating current. For this reason, we should think how to protect the machine and the external circuit from such danger, like the maximum current tolerated in the protective fuses. This test helps also to calculate the short circuit reactance of the machine. We move now to the load analysis of the Axial-Flux Permanent Magnet Generator. As we said before, we need to know the behavior of our machine under different loads conditions. The integrated circuit simulator of EMS allows to run the generator under different load types like resistive load, RC load, and RLC load. More electronic components are available in our circuit simulator, like diode and transistor. The current and the induced voltage of the generator at different loads are collected in the figures of this slide. At the left, we can see the current and the voltage of the resistive load. Both of them have same shift angle, while we can see the two other figures, a small angle between the current and the voltage waveform. This is because of the capacitive load and the inductive load. Under the load operation, important electromagnetic losses will be generated. This can affect the efficiency of the machine and lead to additional costs of maintenance. Hence, those quantities should be studied carefully during the design of any electrical machines. Eddy, iron, and copper losses can be predicted by EMS. Winding losses are shown in figure 24, while the core loss results are plotted in figure 25. As can be seen, the core loss is higher because of the high frequency current produced by the machine. In case that the machine is made by solid ferromagnetic cores, eddy losses can be significant part of the losses. EMS gives us the ability to estimate eddy current loss in any part of the model. Figure 26 shows the evolution of the eddy loss in the rotor cores versus time. In figure 27, we can see a 3D animation of the eddy currents generated in the rotor core versus rotor angle. Electromagnetic losses heat the machine. Therefore, thermal analysis should be included to estimate the temperature distribution, also its evolution versus time. Temperature distribution in the stator winding and housing is shown in figure 28. It reached a value of 44 degrees Celsius after more than 1 hour. Some axial flux machines have a design challenge related to their cooling system because that the windings are located deep inside the machine, which make their cooling more difficult than radial flux machine. EMS can help to solve this design issue using its thermal coupling capability. It is fully integrated within the same environment, as we will see later. Before coming to the end of this presentation, we have dedicated this section to talk about magnetic axial flux forces that can be generated in the axial flux machines. These forces are very high and can produce important mechanical stresses in the ferromagnetic parts. EMS, coupled to structural solver, can help to predict the mechanical deformation caused in the structure of the rotor cores. Figure 31 shows the force density applied in the rotor cores of the studied machine. The deformation results were obtained through the electromechanical coupling analysis of EMS. They show 0.125 mm displacement of the rotor cores. This scale was amplified to make the results readable. The direction of the displacement can be better identified by the vector plots. It is the centrifuge deformation. Also, an animation of the structural deformation can be demonstrated by EMS post-processing plots. Now let's go back again to check EMS environment and see how the coupling to thermal and structural can be done. In EMS, coupled multiphysics analysis can be performed within the same study, so there is no export or import of data. All what you need is to couple your electromagnetic study with one of the multiphysics options, whether it is thermal, structural, motion, or a combination of them. Like here, we can couple magnetostatic study to thermal and structural analysis. Hence, we will get the temperature results and the deformation caused by both thermal stress and magnetic forces. Both steady state and transient temperature can be studied with EMS. Also, we can couple our parametric study to thermal analysis so we can compute temperature results versus different scenarios. In this study, temperature distribution and variation of the machine winding were calculated. Iron and eddy losses were neglected. So we can see the temperature of the winding and the stator housing. It reaches a value of 34 degrees Celsius. This figure shows the temperature variation versus time. While in this study, electromechanical behavior of the machine were analyzed to get the displacement results of the rotor cores. Let's plot the displacement and the rotor cores. We use the finite scale and select one of the rotor. We select one of the rotor cores. Let's define a modified scale. Let's simplify the displacement results times 200. So the formation now is more readable and clear. Switch the unit. So this is our deformation results. Let's convert this plot into vector plot. Switch the view and animate these results. The displacement is in the y direction and toward the second rotor core. Let's go back now to our presentation. Now we come to the conclusion of our presentation. During this presentation, we have seen that however axial flux machines have several advantages compared to radial machines, like higher output power and efficiency, more robust and compact structure, but they represent many design issues and challenges for engineers. EMS, which provided a full solution to handle these design concerns, was used to conduct the performance analysis of few typical axial flux PM permanent magnet generator examples. No load and load conditions of the machines were studied using EMNs coupled to SOLIDWORKS motion. Both output voltage and current were computed under different simulation scenarios. After that, the electromagnetic losses generated in the machine were estimated, and at the end, electrothermal and electrostructural coupled analysis of EMS were used to evaluate the temperature and stresses in the machine. Thank you for your attention, and now I hand over the screen to my colleague Carl to continue the presentation. Welcome.
So my colleague Majdi used EMS software to showcase few simulation results. For example, he showed magnetic flux results, he showed about thermal, he showed about stresses. All this can be achieved using EMS product. Now let's take a quick overview on EMS product, what it offers. So EMS offers electrical and magnetic solvers. In addition to these solvers, we also offer few multiphysics options like thermal, motion, linear statics, and circuits. Thus, EMS software is available in 4 different package options. Electric, which will give you access to electrical solvers, magnetic, which will give you access to magnetic solvers, professional package, which will give you access to electric and magnetic solvers both, and finally we have a premium package which will give you access to all the solvers in addition to the add-ons like thermal, motion, structural and linear statics. In order to get more information on the software packaging pricing, you can connect with me after this webinar. Now let us do a quick recap on EMworks products and their related applications. We can divide EMworks offerings into 2 categories: applications related to low frequency simulation and applications related to high frequency simulation. Within low frequency category, we offer 3 products: EMS 3D, EMworks 2D, and Motor Wizard. These products can be used to design and simulate applications such as cables, insulators, bus bars, eddy current braking systems, wireless charging devices, transformers, and electrical machines. And within high frequency category, we offer one product which is known as HFWorks. This product can be used to design and simulate high frequency applications like antennas, waveguides, filters, resonators, connectors, etc. EMworks offers various free learning resources. With the software purchase or an evaluation license, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our web page and social media channels regularly. We also offer paid customized training sessions to all the users of EMworks software. Anyone who is interested to get more information on our products, including a trial license, quotation, can go to our Contact Us page on EMworks website, select the appropriate category and submit your request. One of our representatives will reach out to you. Before we answer your questions, I would like to thank you all on behalf of EMworks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you.